Okay, so in this second hour, we are going to continue with the material where we left it last Tuesday. So we're going to continue our discussion of ideal flows or of irrotational flows. Now I hope that it was worth on Friday and for the first hours going back again over control volume. Control volume analysis is something which we will continue to use throughout the semester, and is definitely a tool that is important that you develop in the class. Now, some of you may be wondering where I am. I am in fact at a conference at the American Physical Society Conference Division of Fluid Dynamics. So if you are a fluid dynamicist, if you are interested in fluid dynamics, this is definitely a place where in the future you will want to be. So I can show you this year the meeting is in Denver. So in principle, if you see what I see, you should see the Rockies from the city of Denver. Now I will be back on Friday, so any question that either Koen or John couldn't answer, just hold on, and I'll be able to answer all of these. I'll have my office hours on Thursday, 12:30 to 1:30. So if you have questions, then you can come and see me during office hours, or on Friday at our regular lecture time. Now I have just a few announcements. In the coming days, I will post problem set number 4, which will be a very short problem with on vortex dynamics. There will only be a very few numbers of problems in there, which are typical problems which you should have seen about vortex interactions. And on Friday, we will continue discussing inviscid flow theory, potential flow theory, and hopefully we will derive the solution for the irrotational flow around the cylinder. So if you want to go ahead, you can read that part in Kundu. It's chapter 7. Now I don't have my book with me, so I can't tell you exactly which section it is in, but just look for flow around the cylinder and you should be able to find it. Okay, so again, in our roadmap, so we finished deriving all of the governing equations, we discussed boundary conditions, and now we are focusing on a particular subcategories of flows, which are ideal flows. And for ideal flows, the concept that we introduce is irrotationality. So let's assume the flow is irrotational, and by meaning the flow is irrotational, that means that in the bulk of the fluid, we have no vorticity. So we assume that the vorticity is 0 everywhere. In other terms, we're assuming that the curl of the velocity is equal to 0. So we're only looking at flow fields, at velocity fields, which satisfy which are irrotational. Now there is an immediate consequence of irrotationality, which we discussed last Tuesday, and that is that if the flow is irrotational, so you can rewrite, you can take the curl of the vorticity. Now the vorticity is equal to 0, but there's a mathematical expression which allows you to write the curl of the vorticity as the gradient of the divergence of u minus the Laplacian of u. And if we are incompressible, so if we are irrotational and incompressible, then we directly get that the Laplacian of the velocity is equal to 0. Now you recognize that this here, the Laplacian of the velocity, is the viscous term in Navier-Stokes equation, and therefore if the flow is irrotational and incompressible, then it is inviscid. So now you can associate this concept together. So a flow which is irrotational and incompressible is often called an ideal flow, and in that case the flow is inviscid. So let me write it here. A flow that is irrotational and incompressible. This is an ideal flow. So don't confuse an ideal flow with an ideal fluid. You talk about an ideal fluid or an ideal gas when when you have a model for your gas that satisfies the ideal gas law, the PV equals nRT. This is not the same thing. An ideal flow is an irrotational, incompressible flow. It has to do with the flow, not the fluid. So if the flow is irrotational and incompressible, then the flow is inviscid. And therefore, we are justified to say that viscosity is negligible. Viscosity is negligible. Okay, so this is our first remark. Let me box that. And the other one, which is very important as well, is the following. So hold on. This is to consequence of irrotational flow. So we have if the flow is irrotational and incompressible, it is inviscid. And the other one is the following. So we hinted at last time. If the velocity field is curl-free, mathematically, that means that the velocity field derives from a potential, from a velocity potential. That is a mathematical property. Any vector field which is curl-free derives from a potential. So if we are irrotational, then we can say that the velocity field u derives from a potential, so a scalar function, which we call the potential. There is no physics involved in that. This is a mathematical result. This is a mathematical result, and therefore we can write u, if it derives from the potential, we can write u as the gradient of a function. Here u is the velocity field, and phi is the velocity potential. Now, this is not as unfamiliar as it may look at first. You already know this from dynamics or from point mechanics. You can, if you don't see where why an irrotational flow would derive from a potential. Remember, if you replace the velocity field by a force field. Now, a force field which is curl-free, so forget about velocities, forget about fluid dynamics, remember just dynamics. When a force field is conservative, right, that means that a force field does not work along any closed contour. This is the same as saying that the line integral of the force is on the closed contour is always equal to 0. So saying that a force field is conservative is the same thing as saying that it doesn't work along the force doesn't work along any closed contour, which is the same as saying that the line integral, so this line integral here, right, on a closed contour is equal to 0. Now, if this is true, that actually means that maybe you had not introduced that term, but to say that a force field is conservative is actually the same as to say that your force field is curl-free. And you do remember that a force field which is conservative derives from a potential. So mathematically, the origin of the fact that for an irrotational flow, the flow derives from a potential is the same as saying that for a conservative force field, the force field derives from a potential. It's the same mathematical theorem that we apply. Okay, so if we have an incompressible, if the flow is irrotational, it derives from a potential. And now, if on top of that we assume that the flow is incompressible, then we have another interesting result, and that is that the potential is a harmonic function, that it satisfied the Laplace equation. But I'll discuss that in just a few minutes. Okay, so here are our two observations. Now, what we are going to do now is see what equations that we get for an incompressible irrotational flow. And that will lead us to derive the unsteady Bernoulli equation. Unsteady Bernoulli equation. Now, we already discussed one version of the Bernoulli equation, which was a weaker version of the Bernoulli equation, where we simply assumed that the flow was inviscid. So we said that the viscous term in the momentum equation was negligible, but we did not assume the flow was incompressible. Now, was irrotational. Now, assuming irrotationality is a stronger assumption, and we'll see that with that stronger assumption of irrotationality, we also get a stronger version of the unsteady Bernoulli equation. So we start from an inviscid flow. So we have Euler's equation. And so let me just rewrite Euler's equation here. So rho du dt plus u grad u. By now, I'm hoping that you know this equation by heart. Minus gradient of p. We assume the flow is inviscid. And actually, we're not assuming. If the flow is irrotational, unsteady Bernoulli equation, this is only for irrotational flows. Irrotational. So from now on, we only discuss a particular subset of flows which are irrotational. And if the flow is irrotational, then the viscous term is equal to 0, because the Laplacian of u is equal to 0. We just discussed that. And therefore, our governing equations reduce to the Euler equations. And we're assuming that the body force, is conservative. This here, this phi. So now be careful, phi. This phi here will be our force potential, and this other phi here, that will be our velocity potential. So here, this phi is our force potential. I'm not going to rederive what we discussed in the previous period, but if you go back to the lecture on Tuesday, October 10th, then we tweaked the u grad u term to get to the Bernoulli equation. And so I'm going to do the same tweak. Just go back to your lecture notes from Tuesday 10th. And when you do that, then you can rewrite the momentum equation as rho du dt plus the gradient of the pressure plus 1/2 rho times the norm of the velocity squared plus your force potential equal to u cross the vorticity. Now, there are two important things. If we assume the flow is irrotational, so for irrotational flows, then u derives from a potential. So I'm going to rewrite u here as the gradient of my velocity potential. And if the flow is irrotational, then of course, by definition, the curl of the velocity, or the vorticity, is equal to 0. So now note that in the weaker form of the Bernoulli equation, we did not assume the flow to be rotational, therefore there was vorticity. And what we did is we integrated this equation here along a streamline, right? We said that if we move along a streamline, then this vector here is equal to 0. And therefore, we had that this function was constant along a streamline. Now, because the flow is irrotational, then this term is actually equal to 0. So we can rewrite the equation as, if we replace also u by the gradient of phi, then we have that the gradient of rho d phi dt plus p plus, sorry, let me just write in another way, plus 1/2 rho times the norm of the velocity squared plus p plus the force potential phi is equal to 0. Now, this whole term between the brackets, so this rho d phi dt plus 1/2 of rho u squared plus p phi, is a scalar. It's a scalar field. So if the scalar field has a gradient which is equal to 0 everywhere, just think about a function whose derivative is always equal to 0 everywhere. That means that the function is constant. So therefore, we can integrate that and write that d phi dt, rho d phi dt, plus 1/2 rho u squared plus the pressure plus the force potential is equal to a constant. And it is important to note here that this constant is independent on the streamline. It is a constant in the entire field. This is equal to 0. Let me just write here. This is equal to 0 everywhere. Everywhere. So this is a constant everywhere. This is not only constant along a streamline. It is also constant across streamlines. And this equation here is valid for unsteady flows. We haven't assumed that the flow is unsteady. Now, of course, it might be a bit strange for you to see here a mix of phi and u. If you are confused because it seems like there are too many variables, just remember here that u is just the gradient of phi. So this is really an equation for the velocity. So there are a few remarks which I want to do here. Let's do a few remarks. So the first one is just to really highlight that the constant in the unsteady Bernoulli equation is independent on the streamline. So the constant is constant everywhere. Constant is independent on streamline. So in particular, if the flow, if the flow is irrotational, so for irrotational, and if it is not only irrotational, but it is also steady, for irrotational and steady flows, when the flow is steady, that means that d phi dt is equal to 0, and therefore we have that p plus 1/2 rho u squared plus phi is equal to a constant, and this constant is a constant everywhere, and again I'm going to write it is independent on the streamline. So when the flow is irrotational, you can still write Bernoulli's equation for steady flows. When the flow is irrotational, you can still write Bernoulli's equation for steady flows, which looks a bit like the weaker form of the Bernoulli equation which we wrote, except that if we did not assume irrotationality, p plus 1/2 rho u squared plus phi was constant only along a streamline, but if the flow is irrotational, p plus 1/2 rho u squared plus the force potential is constant everywhere. So it's constant across streamline. You can identify the constant anywhere you want, and you can impose Bernoulli's equation between any 2 points. No need to be along streamline. So let me write that. We can apply Bernoulli's equation between, and this is important, any 2 points, right? So you can along a streamline, but it's not necessarily along a streamline. It can be across a across streamline. So there is no need to follow a streamline. Okay, this is our first observation. Now the second observation is, when do we use unsteady Bernoulli equation? So this is always the place to start if you have an unsteady flow which is inviscid. Okay, so unsteady Bernoulli, when do you use it? Unsteady Bernoulli is the place to start for inviscid and unsteady flows. So I can tell you right away when you will see unsteady Bernoulli in lecture, when we'll talk about objects which accelerate in an inviscid fluid. Acceleration means the velocity field changes and therefore it's not steady, so we'll use the unsteady Bernoulli equation there. And later on we will discuss gravity waves. So if you're thinking about wave dynamics in the ocean or else, then you have a large scale flow which oftentimes you can model as inviscid, and it is not steady, it is unsteady, and therefore again in that case the unsteady Bernoulli equation is going to be the place to start. Right, so an important point now is, so we've discussed the unsteady Bernoulli equation. An important point now when we discuss irrotational flow is to note when can we actually assume that a flow is irrotational. So when is this assumption justified? So we'll discuss that now. This is point 4. When can we assume irrotationality? When can we assume irrotationality? So here, this you can read in chapter 7.1 from Kundu. Now, we will not go into too much detail. Oftentimes, it will be pretty obvious whether or not you can assume the flow to be irrotational, but sometimes you will have to guess yourself. And so for that, it is always good to go back to the fundamentals, and an important equation in that is the vorticity equation. So when can we assume the flow to be irrotational? Oftentimes it will start by looking at infinity and seeing whether the flow is actually irrotational at infinity. So let's consider a flow which is irrotational at infinity. Right? If you want your flow to be irrotational, in particular, it needs to be irrotational at infinity. And now, for a flow to be irrotational at infinity, this is not so unusual. So in practice, this is often the case. This is often the case, right? So think, for instance, about most of the time what we had was a uniform flow at infinity, right? And the flow was either uniform because it was at rest, or because there was a constant flow field at infinity. But in any case, the flow will be in uniform irrotational at infinity if it is uniform at infinity. So a uniform flow at infinity is irrotational, and that includes irrotational, and that includes most of the flows that we've seen, in particular the flow where u is equal to 0, so is at rest at infinity, or this is often the case in the lab frame, in the frame of reference in the lab, if you have moving objects, or even if you are in a wind tunnel, for instance, and the flow when you go to infinity is simply equal to a constant, right? So in either of these cases, the flow at infinity will be irrotational. Now, if the flow so to have an irrotational flow, we need the flow to be irrotational at infinity. If the flow is irrotational at infinity, then it will have an important consequence if you write down the vorticity equation. So from the vorticity equation, remember that, and now I'm going to be talking about flows in 2D. Okay, so from vorticity equation for 2D. Actually, hold on. Let me just go back here. Let's write the vorticity equation. The vorticity equation is the material derivative of the vorticity is equal to the vorticity dot grad u plus mu times the Laplacian of omega of the vorticity. So from this equation, we see that if we assumed that the flow was irrotational at time equals 0, so if we assume that the vorticity is equal to 0, say at time t equals 0, then this equation becomes the material derivative of omega of the vorticity is equal to 0. And therefore, vorticity is only transported, right? So the vorticity of a material element remains, because it was 0 at infinity, it will remains 0. So if the flow is irrotational at infinity and there was initially no vorticity in the field, then vorticity is just transported, and therefore it remains 0. Now the only problems we will have is if vorticity is created. Now from this equation we know that vorticity, if there was no initial vorticity, then vorticity is not created in the bulk. It is just advected. One thing where vorticity can be created then is the boundaries. So the only place where vorticity can be created will be at no-slip boundary conditions on solid walls. So here vorticity will be only created at a no-slip boundary condition, at a no-slip boundary. So this would happen at solid, I should write at solid walls. And this is, of course, a viscous effect. This is a viscous effect. So if we assume the flow to be inviscid, then no vorticity is created at the boundaries, because we'll just impose a no penetration boundary condition and not a no slip boundary condition, and therefore we don't create vorticity, and therefore the flow will remain irrotational. So if the flow is inviscid, then there is no creation of vorticity at the walls, and therefore we can assume that the flow remains irrotational. Okay. So keep that in mind. The important time in the lecture in our class where this concept about vorticity being created at the boundary and diffusing, that will show up again when we start discussing boundary layers. But for now, keep in mind that if the flow was initially irrotational at infinity, and if we neglect and if we assume the flow to be inviscid, then therefore it will be enough to say that it is irrotational everywhere in the bulk. Okay. Now the last point which I want to discuss for irrotational flow is, so if we have an irrotational flow, what boundary condition do we impose at walls? So what boundary condition for irrotational flows? Now whenever we'll be talking about irrotational flows, if the flow is irrotational and incompressible, we've seen that it is inviscid, and therefore we cannot impose a no-slip boundary condition. So the only boundary condition we can impose when we're discussing in this discussion about irrotational flows is the no penetration boundary condition. So in that case, what we will impose the no penetration boundary condition. Remember, the no penetration boundary condition has to do with mass conservation at the boundary. So what we are saying is that the normal component of the flow velocity field at the surface needs to match the normal component of the velocity of the solid wall at the surface. So this is for a location x on the surface S, on the interface S, and n here is normal to our surface. Again, in particular, at the surface of an object which is not moving, so if S, the solid S, is at rest, then the no penetration boundary condition is simply that the normal component of the velocity, the normal component to the surface, normal to the surface of the velocity is equal to 0. If the object is moving, then we have to match the normal velocity of the flow with the normal velocity of the solid surface. Okay, so now what we're going to do now is to detail how we can build solution to the momentum equation when the flow is irrotational. And so the concept which we'll introduce is potential flow, which essentially you have potential flow theory when the flow is incompressible and irrotational. So for an ideal flow or potential flow is essentially the same thing. And we are going to discuss that first in a particular geometry configuration, which is for two-dimensional planar flows. So that is, I believe, our fourth section. Let me just check that real quick. Nope, it is the third. Okay, so number 3. Potential flow theory for two-dimensional planar flows. So the theory we're going to discuss now is really the theory which essentially was the foundation of modern aerodynamics. So here is what we're assuming is that the flow, so we assume an irrotational, incompressible flow. Again, this is equivalent to saying that the flow is ideal, and this is equivalent to saying that we have a potential flow. So why is it important? So from irrotationality, we get that the curl of U is equal to 0. So the flow is irrotational. That means that the curl of U is equal to 0, and therefore that the flow velocity field derives from a potential. So u is equal to there exists a function phi, which is the velocity potential, such that u is equal to the gradient of phi. And if on top of that the flow is incompressible, then that means that the divergence of u is equal to 0. And therefore, if we combine the two, then we have the divergence of u, which is the gradient of phi, equal to 0, and the divergence of the gradient is equal to the Laplacian of phi is equal to 0. So for ideal flows, not only does the velocity field derive from a potential, but that potential has a very typical mathematical let's say property, because it satisfies the Laplace equation. And we know, which is another way of saying it's a harmonic function, and therefore we know many functions. We have the analytical tools to build a solution to Laplace equation. So this is a very important observation. For ideal flows, the velocity potential phi, so for ideal flows, our velocity potential phi satisfies the Laplace equation. In other words, phi is a harmonic function. So what we'll do in the following is we will introduce special flows and their harmonic potential, the potential which are associated with that. Now we'll discuss that again later on in the class, but what is important for you to note is that this equation, so the Laplace equation, is a linear equation. So if I have one potential, let's call it phi1, and I have another potential, let's call it phi2, then if I just add them up together, so phi1 plus phi2, it is still a harmonic function. It still satisfies the Laplace equation, which allows us now to build up solution which allows us to compute velocity fields for ideal flows simply by superposing their potentials. Okay, so we'll discuss typical flows and their potentials. So the first important flow to know. So all of these flows you have to know. You have to know the vector fields in say Cartesian and in polar coordinates. You have to know the velocity field components, and you have to know the potentials. You need to know these. And the first one we'll discuss is perhaps the simplest one, and that is a uniform flow. So what is the potential of a uniform flow? Now note that a uniform flow is an irrotational flow. The velocity vector is the same everywhere, so the curl is equal to 0. So what is a uniform flow? A uniform flow is just the velocity field at any location in the x direction is equal to a constant, and in the v direction is equal to another constant. So if we write that the gradient of phi is equal to those two constants, then we have the two equations, partial phi partial x is equal to u, and partial phi partial y is equal to v. So we can integrate these, and when I integrate these, I get, when I integrate the first one, I integrate at constant y, so I get phi is equal to ux plus a function which is unknown of y. And when I integrate the second one, I get that phi is equal to v times y plus an unknown function of x. Now because phi is a function and it is defined, one potential which can be written in both forms will simply be the potential phi as a function x of y equal to x plus v y. This is the potential here, corresponding to the uniform flow U, where the x component is capital U and the v component is capital V. And this is all written in Cartesian coordinates. Cartesian coordinates. It would be a good exercise for you, you've done that before, but to rewrite a uniform flow in polar coordinates. So let me just leave it up to you. So in polar coordinates, I'll let you write both the velocity field and the potential. Okay, and the potential as a function of r and theta. This is our first typical flow. It's an important flow because we'll be using it in the future again. Now, the second flow is the potential flow around a point source or a sink. Okay, so and I'll discuss just in just a second what a source or a sink is. So 2, let's compute the potential flow around a point source or a point sink. Now I think you will understand in a second what it means. Now note, there's an analogy which I want to make here, is that what we are doing now is we are introducing the building blocks of potential flow theory. And so we're introducing 4 different Lego pieces, if you want: the uniform flow, the point source sinks, the rotational vortex, the potential dipole. And then once you understand these basic flows, you can just build much more complicated flows by just adding them up. So it's important that you know exactly what your different building blocks, what your different Lego pieces can do. So let's do sources and sink. And we will first do the derivation of the potential flow and the velocity field for a source. Now, what is a source? A source is something a little bit weird, because a source is a flow where you create volume, where you create mass. And so we discussed that usually you cannot create mass, you conserve mass. So what you will find is that usually a source, you will have a source where you create mass, and it will always be associated with a sink where you suck in mass, because otherwise you create mass, and that is not physical. But it is nevertheless a very important flow to be able to represent. So let's assume that we have the following. So we have a point. This point is, let's say, at the origin for now. So let's say here, this is the origin. And what we have is that we have volumetric flow rate Q coming out of this point. So you imagine, this is weird, but imagine you have a point, it's in 2D, and out of this point, you have flow that start to be created from this point, and just volume just comes out of this point. So the flow, if there is nothing else, the flow will be radially symmetric, and will just flow in the radial direction. So here we have a source of volumetric flow rate Q. Flow rate Q. So that simply means in this case that we created a Q amount of volume. So in this case, if you think about the continuity equation, which is mass conservation equation, here we always have the continuity equation, we all expect it to be equal to 0. But actually in that case, this is true everywhere except at the origin, because at the origin we create volume, right? We have mass coming in through this one point. So really what we have is that the divergence of u is equal to a delta function. So this is a function which is equal to 0 everywhere except at r equals 0 times our volumetric flow rate q of our source. So let me write this. This delta function simply means that for r not equal to 0, so anywhere in the bulk of the fluid, so anywhere here, we have the incompressibility condition, so we have mass conservation, except for r equal to 0, the divergence of u is equal to infinity if you want. We create volume. Okay, I see that it's been 45 minutes now, so we'll finish that on, well, let me just finish writing our equation. So we have that the divergence of u is equal to 0, so in terms of the potential, which is what we were looking for, we have the Laplacian of the potential, which is equal to q, the value of the source, times a delta function. And this is a well-known equation for which we know the solution. So we'll write this solution on Friday. On Friday we'll discuss sinks, sources. We'll rediscuss irrotational vortices. So you'll see irrotational vortices a second time, and we'll discuss also dipoles.